So without further ado, it's time that we move on to introduce our fellows to you. And I'm delighted to introduce our first fellow, Professor Mohamed Abdel-Aty from the University of Central Florida. And the title of his presentation is Next Generation Roads, AI, Big Data and Computer Vision Applications. Welcome, Professor.
Thank you.
Let me just,
Thank you. Okay, good morning, and it's a pleasure to be back here at Loughborough. You know, first, University of Central Florida, I hope you guys know where it is. I know Nicolette know. Other than that, any guesses? University of Central Florida? Center of the state in Orlando, right? So if you ever went to see Mickey Mouse, we are very close there. So at least you know where we are. We are actually the largest university in Florida. We have more than 70,000 students. So it's really, and it's developing very, very fast, including in transportation. We focus, one of our focus areas is AI, and we have recently established a center with a lot of support from the president of the university to establish. I am part of this center that will be a multidisciplinary AI center, and we will hire 20 more professors with specialization in AI as part of this effort. So you can see it's very important up and coming topic. I had a problem to think how I'm gonna, present in 20 minutes. I'm a professor. The least, the shortest class is 50 minutes. So I'm used to talk for 50 minutes. It's okay to present a paper in 15, 20 minutes, but if I have a lot of things to say. So I will go a little bit fast. I will give you a flavor on bits and pieces of projects in my team. So I'm not going to give you a lot of philosophy. I'm just going to tell you what we are doing relevant to AI, but I look forward to the panel that I can talk more about other issues and some of my opinions about where we are with respect to AI. So, and also when you say AI, it's a very big term, right? I mean, there are, natural language processing is AI. Expert systems AI. I mean, there are a lot of things that we worked with in the past, like text mining of crash data, reports, etc. This is all AI, but today I am mostly talking about machine learning and deep learning. And this is part of AI. It's definitely not the full picture of AI. And I'm mostly going to talk about better prediction. I'm going to talk about the new data, including collecting new data, not only using new data, but collecting new data. And I'm going to give you some applications that we have developed. If we talk about the data in transportation, by the way, I'm mostly safety person. So I'm going to kind of alternate between safety and mobility. And really, a lot of what I'm going to say about safety is very relevant to mobility. So, but, just bear with me because I cannot deviate a lot from safety. This is really my passion. So it's going to be safety, mobility, and not only AI and mobility. So we have been using, a lot of data. If you look on the left side, the infrastructure data, the roadway design, roadside, etc. We use now a lot of probe data. There are a lot of ITS generated data. I'm going to explain this in a minute. Signal timing, weather, CAV, all these are generating data, but there are also new types of data that do not have the standard formatting that we are used to. So there are a lot of now images and videos coming from computer vision applications. Smartphone is generating data, LiDARs, Internet of Things. There is a lot of data coming also, and they are not, as I said, have different types of formats, different shapes, different sizes, that we need to combine all this or fuse all this and make sense out of it. So it's an opportunity, but a challenge at the same time. On the right side, I talk a little bit about the two types of machine learning models, the neuron-based models, and I'm going to elaborate more on that. And on the right side, I'm talking about the tree-based models. Both are considered machine learning models. And then one of the problems that we face with this such large data is the imbalance of the data. So for example, if I'm looking at a segment of roadway and I have per year 10 crashes, I have thousands of observations where there are no crashes. So if you want to classify the condition of a crash, you are trying to classify 10 versus 100,000. So this caused an imbalance in the data, and therefore we use AI also to generate synthetic data in order to balance the data. And I can elaborate on that also if needed. This is the data that I have in my lab that have been growing over the last 5 or 6 years. On the left side, this is mostly the traditional type of data, which are the crash data, the citation data, the geographic data, like the census data, etc. But mostly to the right, you're going to find the new data that we have been using, and some of them is real time. And we have a direct connection, fiber optics from our DOT to my lab, giving us every 30 seconds data. So all the roadways in Central Florida, the microwave detection, the signal indications, Bluetooth detectors, etc., is fed live into my lab. So we have also the ability to do real-time applications using this data, and I also will talk about it more. You also can see the ATSPM here. Sorry. ATSPM here, this is a signal system, which basically captures everything happening at the signal. The signal indication, the pedestrian crossing time, a pedestrian, press the button to cross, all the details of the signal operation is also fed live into our lab. Cameras, just to give you an idea, in Florida, the state where I live, there are 18,000 CCTV cameras. In only the Central Florida area where the university is there, we have 600 CCTV cameras. We have access to about 110 CCTV camera live. And we are using these video feeds from CCTV to do some video recognition, and I'm going to also talk more about it. We have floating car data, like all the buses, links, and the UCF shuttles. These are buses. We have GPS reading every 3 seconds from all this live. And I started to collect also the third-party data, because this is coming and very important. All these companies that are collecting data from us, as we use Google Maps and as we're using other systems, they're using us to generate data. They are mostly selling this data. So we have the here data. We have Wajo. Wajo is a British company. Wajo is collecting data from car companies. They say this is connected vehicle. It's good data, but I'm not sure it's really connected data. But it has definitely more than only GPS data. It has the brakes. It has other data from the vehicles. We did buy some months of this data from Wajo. Analytics is also a third-party data. It's mostly naturalistic data. So it's a company that is helping agencies to train their drivers by monitoring the vehicle, by having 2 cameras on the driver and on the road to capture also videos. And we have also live access to this data. So we can use it as a naturalistic data and other applications. Strava is an exercise application. So usually joggers and bikers use it. So it gives us also some indications of the bike routes and the bike activities, as well as some of the pedestrian. All right. So just I thought I'd spend a minute here, because just to give you a flavor of the types of data that we are getting. So let me quickly tell you, okay, so how do we use AI in collecting data? So I mentioned the CCTV. So for example, if you look at this map, the orange dots are the RWIS stations, road weather stations. The little blue dots are the CCTV locations. So you can see that the CCTV has more coverage of the network. By the way, the RO is not necessarily on the road, but the CCTVs are on the road. And there are space between 1/2 and 1 mile. So what we are doing is that we are training machine learning models in order to capture this image and transfer it to us into weather condition, both intensity of rain and the wetness of the pavement. These are very important for safety, right? So therefore, we have every mile an indication of the weather condition at every point. So if you work in accident analysis, you know that weather is very important component of the factors contributing to that. So this is live. So as we get the image, it enters into our algorithm that we already trained on images of different weather conditions to give us the weather. Not only that, it connects to the other locations with the spatial. So if a camera is not pointing to the right direction, the camera upstream and downstream will give us an indication that we can infer what's happening in the camera in between. So this is AI used for data collection. You know that your smartphone is generating, your smartphone has 8 important sensors. The most important are the GPS, the cellular position, the accelerometer, the magnetometer, and the gyroscope. So basically, you can get trajectories, you can get elevations, you can get acceleration, you can get location, all from your smartphone. So we developed an app where we can collect all this information, process some of them on the edge, process the other in the cloud, and send information to drivers in the concept of I2V or V2V and P2V. Right? Because we thought that pedestrians are out of the equation with respect to the connectivity. Because so a connected vehicle uses a roadside unit and uses what we call an onboard unit, RSU and OBU. A pedestrian will not be carrying an OBU, but a pedestrian will be carrying a smartphone. So if we emulate the OBU, the onboard unit, with the smartphone, you can collect information from pedestrians, you can send warning and information to pedestrians. So the pedestrian becomes back part of the connectivity of the network. So we use the smartphone as this mean to warn pedestrians if a vehicle is coming, say, at night toward them, or they are very close or distracted. So if I'm distracted and looking on my phone, and then suddenly pops a warning, there is a vehicle coming, then the pedestrian will become part of the safety scheme of the connectivity. So we use that. Not only that, we use the trajectories to train machine learning models so that I can predict the trajectory of vehicles, whether they're going to turn or not, so that I can accordingly connect it to other applications in the concept of connected vehicles. So this is data collected from smartphones. Just for a minute, to pause for a minute, please, when I'm 20 minutes, warn me, because I will go. Right. So I think maybe I should have put this slide at the beginning just to give you context. So when we talk about machine learning models, we are mostly talking about, as I mentioned, tree-based, neuron-based models, such as, and you hear this a lot now in the literature, random forest, SVM, extreme gradient boost, feed-forward neural network, so neural network family. This is all part of what we call machine learning. If you want to talk about deep learning, we use them interchangeably, but mostly we are talking about recurrent neural networks, such as GRU and LSTM. And one of the PhD students, I think yesterday, was talking about LSTM, and convolution neural network, graph neural networks, and transformers. So that just to give you the terminology when we talk about machine learning versus deep learning. So if we look at traffic, there are several applications of different models for different purposes. So in traffic, we exhibit a lot of spatial dimension issues as well as temporal dimensions issues, right? So I give you here just some expertise of what we use. So we found, of course, we try different models and then we say, this is the best for this particular situation. And this is part of the challenge, right? Is that you have a lot of data, you have a lot of different techniques. So which one is suitable in which application? So I'm just giving you some feedback about our experience. So in the spatial domain, we found that the convolution and the graph neural networks are doing well. And in the temporal domain, the LSTM, because the LSTM by definition has the long and the short-term side of it, and also the gated recurrent networks. So what type of applications we use? Now I'm talking about prediction. Remember, I said I'm going to talk about the data, I'm going to talk about the prediction. So in the prediction, we use short and long-term horizons to estimate the speed and the volume. So now we were successful to predict up to 60 minutes travel time and travel speed and traffic volumes on freeways, and up to 30 minutes on arterials. So based on the current real-time data that we are receiving, we can predict the next hour what we expect. So this is very useful in applications like Google Maps, for example, to be able to predict the future traffic condition. We looked into intersection volumes, prediction of intersection volumes, and this had a very important application. This is actually applied because what DOTs do now is that they put sophisticated systems in order to capture the traffic volumes, adjust the signal timing in real time, and other applications, right? So they put cameras and software, etc. To give you an indication, to give you a little value, this costs approximately $25,000 per intersection, just equipment to capture what's going at the intersection. All right. So what we did is we told DOT, let us save you some money. If I have a corridor and I have sequence of intersections, instead of you installing this system at every intersection, can I remove one from the middle between two and estimate it using machine learning? And if we can do this accurately, you can remove the equipment, put it somewhere else. So I'm saving every other $25,000. So, to give you an indication, we have more than 1,000 intersections in only Central Florida. Right? So this has a practical, immediate applications in saving money. So we did that. SPAT, which is the signal phasing and timing projection. This is we are predicting the best signal timing up to 6 cycles in the future. Why this is important? It's important for efficiency. It's important for connected vehicles. Because as the vehicle is approaching, we want to tell the vehicle whether the traffic light is going to be green, or you need to slow down, or you need to speed up, or whatever, right? So this is also an important application for connected vehicles. For crash prediction, I'm going to talk a little bit more about it if I have time toward the end, but this is a different story. There is also the concept of reinforcement learning, and this is mostly for sequential decision-making that we use. So it is not like one prediction for one thing, but it is a continuous prediction that updates sequentially. And this is important in things such as cooperative driving, which is part of the connected vehicle, collision avoidance systems. So now when we talk about connected and autonomous vehicles, these are, reinforcement learning is one of the ways to develop these algorithms. And these are things that we are testing in driving simulation. The concept of cooperative driving, which is how a group of vehicles are cooperating to achieve something. Like, for example, how they are crossing the intersection without colliding with each other because they are talking to each other. So this is the concept of cooperative driving. IoT, we developed a system for a smart corridor, and we used all the sensors that are listed here: cameras, LiDAR, smartphones, UWB. By the way, UWB is a sensor that you have now on your cell phone, on your smartphone, but it's not open. So neither Samsung nor Apple are opening it yet, but it exists on your smartphone. So we used the system not from a smartphone. We bought a UWB system, ultra wideband system. So how to fuse the data coming from all this to have a better data from a corridor and intersections, and how you use the best data and fuse it for different types of applications. Of course, machine learning is in the middle of all this. All right, let me shift quickly to video data processing, because I know that this is, or I think, not I know, I don't know anything, but I think that this is big part of the future. I always, when I talk to, DOT and try to convince them something, I say, you have 18,000 cameras. These are 18,000 eyes on the road 24 hours. And the brain is the machine learning. So imagine you have an expert looking, 18,000 experts looking at the road all the time. Imagine what they can do. So I think camera, of course, it has problems, right? Because bad weather, night, we can discuss, how to, but in general, the cameras are always on the road. And all what we use these cameras is for traffic management, monitoring, so the operator look at them. Can the operator look, in Central Florida, for example, they have 1,600 cameras. Can the operator look at the 1,600 cameras all the time? No way. How many operators you need? So we need a way to identify which cameras are looking at a serious situation and what is the interpretation, so that the operator can make a right decision or automatically make a decision, right? So that's why I believe in computer vision, and a lot of my work is going toward this direction. And I listed here some of the applications of computer vision. Now, there are so many companies, particularly in Canada and Australia, that are doing computer vision. I evaluated all of them, and none of them is good. Seriously. Okay. So industry, academics usually don't talk very well together, and industry can sell things very nicely, can have very nice brochures, and they can go and convince, DOT to install them. I evaluated the systems for our DOT, and most of these systems have problems, particularly for safety. I mean, using a computer vision application to count cars, no problem. It's not it's not difficult. But using a computer vision system to determine the conflicts and the safety potential is not done right. I'm telling you. So I can give you a flavor now, but we develop much. The problem is not I'm not a businessman, or else I would have left the university and took what we developed and commercialized it. This is my main problem, right? So I need somebody with a business, seriously. I mean, if any one of you is really a business oriented, come and work with me, and then you take this stuff and commercialize it. But I'm not good at this. I'm not at that age, at this age anyway. So we developed two systems. One is called RSys, and this is based on drone videos. Okay, so you have two types of videos, right? You have the drone which looks down. This is the easiest, right? Because you have, and there is no occlusion. You're looking down, you see the vehicles in 2-dimension, easy, no occlusion, right? And that is the optimum for safety, because you can see exactly the gaps between cars. You can calculate the surrogate measures such as TTC, PET, and all these surrogate measures. Easy, relatively easy. But I'm going to tell you what the industry do. All right. So, for example, so I list again some of the applications that we're using. This actually is a software that we developed with a user interface and everything. But it's a software. We use it, right? So we go and get a video of a location. Usually the drone flight is about 20 minutes. If we need, we fly it a couple of times. If we need longer sections, because the drone has some rules, how high you can fly, etc., we have in this program the ability to stitch multiple videos so that you can look at a longer corridor if needed. So we have this ability also. So here, for example, is a major intersection. And on the left side, you can see the crashes that happened at this intersection. On the right side, you can see the output from the RSys system that shows us what we call the TTC, the time to collision, which is an indication of safety. As vehicles come closer to each other with a certain limit, we consider this a conflict. And the speed profile on the right side. So yeah, I missed this, but anyway, so we can get cues, we can get turning movements, we can get a lot of stuff. We can, as I said, get these measures from the. So therefore, we can, you can see from the conflicts, for example, on the east-west, there are a lot of rear ends, basically, right? So there are a lot of red approaching the intersection from the east and the west, right? And if you look at the crashes on the left side, there are indeed a lot of rear ends. It's expected. So you can diagnose an intersection with few drone flights rather than waiting 5 years to collect crashes and people are dying and damage is happening in order to determine there is a problem. So you can do it in 1 week. And you can evaluate this intersection in another week. So you say, okay, I'm going to adjust the signal timing, put a warning sign, do something, right? And then you fly the drone again and you make sure that the problem is gone. How long does this take in safety, real safety evaluation? It takes at least 6-7 years. Because you have to collect a lot of data, then you have to identify the problem, solve the problem, then you have to wait until you have a lot of crashes, another 2-3 years, and then do a before and after stuff. You can do this in 2 weeks, right? So you can see that how computer vision and machine learning can make it very efficient and very quick because we don't have the resources to wait years to solve that. The other system based on the CCTV cameras, so it has an angle. So it's not now looking from the sky down, it has an angle because CCTVs are on the side of the road, right? So CCTVs, which you see in most applications in commercial now, they have these bounding boxes, right? And therefore, this bounding box has a lot of problems, right? Because this bounding box, number one, does not turn. Number two, every computer system is based on the center of the bounding box, and the center of the bounding box is not the location of the car that collide with other cars. The edge of the car, the mass of the car is what's in it. So the bounding box has many problems, many flaws. So therefore, what we are doing is that we're actually looking at, if you see the image in the bottom is the traditional approach, although the bounding box is pretty tight, it's pretty good compared to what you see regularly. But look at the upper figure, you can see that it's a mask. It's the important locations on the cars that we are monitoring or the trajectories that we are getting in order to calculate the PTC and PET. This is where I said, you can evaluate the location. So here, for example, you can see clearly that there is a conflict between the bicyclists and the vehicles at this slide. And the solution is very simple. The solution is to prohibit right turn on red at the signal. So there will be no conflicts between pedestrians and bicycles, vehicles and bicycles, right? So a solution done. You fly the drone a couple of times, you find the solution done. This problem is solved. You don't need to wait until a couple of bikes are killed. 20 minutes, okay, right? So this is solved. I was going to talk about also computer vision from the aspect of the vehicle in a warning system for pedestrians. You can see a pedestrian walking through the parking, and then the camera is detecting the pedestrian and giving a warning to the driver. So this is another application. Pedestrians. So we train machine learning based on these CCTV images to identify whether the pedestrian is in the right spot or in the wrong spot, like in the road, for example, or jaywalking, and accordingly warn the driver. This is 90% accurate. So 90% we can warn the driver of the presence of pedestrians. This actually is a very interesting work also where we actually looking at the pedestrian not as a bounding box, as I said, but as a human. So basically we are looking at the pose of the pedestrian, the different important parts of the pedestrian, the head, the arms, the leg, the speed, etc. So based on how the pedestrian about to cross is looking, if the pedestrian is pressing the call button, we train machine learning models to tell us where this pedestrian is about to cross during a red light for pedestrians or waiting patient. You can train a model based on the behavior of the pedestrian about to cross to tell us, and this is 87% accurate. So this is important for safety of pedestrians crossing in a product. So again, we are bringing the pedestrian into the equation. I will wrap up because I wanted to talk about the safety side. This is an award-winning system. Maybe I can have time in the panel to talk about it, because it's really a big deal. This was a system for predicting real-time safety problems 5 to 15 minutes in advance, so that the traffic management center can respond with ITS strategies to calm traffic if we are predicting a possibility of a crash. This, by the way, we achieved 82% accuracy. 82% of the time, we say there is a crash in the next 5 to 15 minutes, and it happened. 82% in real time. This took a really very prestigious award from USDOT. They gave us a big cash award, by the way. I worked with students and the competing teams, the likes of Ford Motor Company, Uber. This is the level that we were competing. And I was working with students, non-funded. And then we got this cash award. So I can talk about it more, but I have some images from the system itself. This is running live in our lab also, and in the traffic management center of DOT. What I'm trying to achieve is the data analytics part in the middle, and a lot of the video things I talked about in conjunction. So I know what's happening on the network. And this, by the way, safety and operation, you can do both of them. And then you can click on an intersection and get the camera and do whatever you want with the images that you're getting with the camera at the same time. So it's a holistic system. So in my view, just to wrap up, is now we are moving toward a more proactive systems that can project, expect, and accordingly do something, right? So this is expert system, you can call it. It's based on machine learning models or deep learning models, but we are very data hungry and very data intensive to project and therefore proactively address safety, operation, and other problems. I talked about data. We have very rich data, the prediction using machine learning, getting better and better. And therefore we can achieve better operation and safety. And we also have timely communication, at least with the mobile phone, if not with other connected vehicle systems. So I think this is where we are heading in general, but of course there are many specifics that we can talk about. So sorry, this is the fastest I can go. This is the shortest presentation I can make. So thank you very much.